Hey all, welcome back to the second half of Chapter 10. We're going to continue from where we left off after defining a lot of the different kinematic variables of rotation and kinematic equations. Take two as they apply to rotational motion. And so now I want to talk a little bit first about kinetic energy and then defining torque and a little bit with work, and then we'll wrap up Chapter 10. Keep in mind, again, I'm giving kind of the basic information in these videos, a few simpler examples, and then you'll see more complex example problems in separate videos. All right, so kinetic energy is equal to 1/2 mv squared. That's translational kinetic energy, the way we've already defined it, right? So for any single point mass moving with some speed v, it will have 1/2 mv squared worth of kinetic energy. Now let's take that same point mass, that same object, and have it move around in a circle. So as it moves in a circle, it still has 1/2 mv squared worth of kinetic energy. But now let's try to think about, what if we have a more complex object, say a tennis ball that's spinning, or maybe an easier one to think of is like a bike tire. If you have a bike tire that's spinning, it's really a bunch of different chunks of mass all spread out, right? All the different tires and spokes, the rim and everything like that. And so to find the total kinetic energy of the whole thing, you'd have to kind of add up all those little chunks of mass. So let's do that kind of in a derivation type manner, but kind of a simplified derivation is what we're going to go with. So let's take a second mass now we've added here at some different distance r2, right? So its kinetic energy would also be 1/2 mv squared, right? But the thing is, it's going to be moving at a different v than the other one since it's at a different r. Even if they're moving together with the same rotational speed, they're going to have different translational speeds. So we want to tie everything back to rotational speed. For a rigid object like a tire, even though the outer edge of the tire and the inner part of the tire might be moving at different linear speeds, their rotational speed is the same if it's a rigid object. So let's replace then v with r times omega, because we know v equals omega times r for any object, right? Moving in rotational motion. So then for these two objects, our kinetic energy is 1/2 m1 r1 squared times omega squared. And then for the second one, it's 1/2 m2 r2 squared times omega squared, where these omegas are the same, but the m's and the r's are different. So again, this comes from v equals omega times r, so v squared is omega squared times r squared. That's the substitution we made here. So now factor out the 1/2 and the omega squared, since those are constant, and what we're left with is that the kinetic energy for this rotating object is going to be 1/2 this thing, this masses and radiuses, times omega squared. Well, what we find and what we're going to define really is what we have left in here, m1 r1 squared plus m2 r2 squared. And if you had 3, 4, 5 different things, it'd just be plus m3 r3 squared plus m4 r4 squared and so on. We're going to define that as a new variable. So again, if you have a third mass, you can add m3 r3 squared. If you had a fourth mass, you could do the same thing. And we're going to define this inside object as a new variable known as the moment of inertia. So this right here, this combination of mass and radius values, tells us or quantifies for us how much inertia an object is going to bring into a system, the amount of resistance it's going to have to rotation. So we can redefine then kinetic energy as being equal to 1/2 1/2 I omega squared. So for translational motion, it's 1/2 mv squared. M being the inertial unit in translation, or v being the speed. In kinetic energy, it's 1/2 I, moment of inertia, times omega, angular velocity, squared. So it takes the same exact form, 1/2 the inertia piece, the speed piece, squared for both of them. So moment of inertia for point masses is defined as m1 r1 squared plus m2 r2 squared plus m3 r3 squared. And you can do that for as many point masses as you have. And that's the moment of inertia. Now, if you have an object that's not a single point, the way you go about figuring out what its inertia is by doing calculus. You can do an integral over the volume of the object to figure out what the adding up of all of the little m's and r's at different r's for a given object is, and you find these equations for uniform objects. So a cylinder is a very common uniform object that we see. If it's solid, since r varies all the way from 0 out to the very edge, your moment of inertia is 1/2 mr squared. Notice for a thin-walled cylinder, if all the mass is at the outside, its inertia is actually double that of the solid cylinder, which sounds weird to people, but again, this is assuming their masses are the same. It would be double because the mass is further away. It offers more resistance when you have more mass further away. All right, you can have a solid sphere like a baseball or a thin-walled hollow sphere like a ping pong ball. Different values that they have. You can have something, here's like a door, right? Where the axis is at one edge and you're going to open the door. It's 1/3 ma squared. It doesn't matter how tall the door is, just how wide the door is that affects its inertia. Different rods, and you can look up other shapes online as well. So that's all fun and good. That's telling us how we find the moment of inertia for just a point mass is mr squared. If it's a different type of object of a uniform shape, you use one of these equations that you'd look up in a table, or on an exam I would actually give them to you. But there's times where you don't have either of these situations. You don't have just a point mass, and you don't have a nice convenient setup like you see in all these equations. Notice, like the solid cylinder, this axis is going exactly through the center of the cylinder, right? What happens if your axis was out here at the edge and the cylinder was rotating around? Sometimes you'd have something like that. Same thing with a ball. What if the ball's out on a string and I'm swinging it, right? If it's a solid sphere, but now it's some distance away from the axis of rotation. The axis isn't just through the center. How do you figure it out then? Well, you find the moment of inertia using something known as the parallel axis theorem. What it tells us is that this moment of inertia of any object just is equal to whatever its moment of inertia is through its center of mass plus its mass times however far away its new axis is from its center of mass. Okay, so interesting. What does that mean? Well, let's say we had a spherical ball, okay? I wish I had my tennis ball with me, but I don't. So imagine I have a ball right here. It's solid. So the moment of inertia, let's check. Its moment of inertia, yeah, 2/5 mr squared if it's an axis through the center. So if it's rotating like this, like a globe or something, its moment of inertia is just equal to 2/5 mr squared, where r is the radius of my sphere. Okay? Now, if I'm going to take that same ball and have its axis be over here and rotate it around the axis like this, now its moment of inertia is going to be 2/5 mr squared, where r is still the moment of inertia, or excuse me, still the radius of my ball here, plus m, the mass of my object, times h squared, where h is the distance from this axis to the center of my ball right here. So h would be the distance between those two. That's the parallel axis theorem. Okay, so sorry, that's the parallel axis theorem. I center of mass, which is usually going to be one of these equations, plus mh squared, where h is the distance between the axis through the center of mass and some new axis some distance away. Okay, so let's try dealing with this idea of moment of inertia. Here's a problem that I want you guys to try. I have the same exact rod here, all right, of distance L, length L, separating two identical masses, M1 and M2, which let's just say they both have the mass M, all right? I want you to tell me which of these two is going to have a larger moment of inertia, an axis through M1 or an axis through the center of the rod. And I want you to prove it to me using an equation. Pause the video, give it a go, let me know. All right, hopefully you paused the video. I paused my recording to take a drink of my coffee, so hopefully you paused as well, and let's see what we got. So let's keep this in mind. Now, moment of inertia, we said to consider these to be point masses. So it's just going to be m1 r1 squared plus m2 r2 squared and so on. In situation A, notice m1 is on the axis. So what's its perpendicular distance? 0. r1 is 0. R always represents the shortest possible distance from the axis to the mass. And I'm going to do another example video with this to try to help it make sense. But yeah, M1 is a perpendicular distance of 0 meters away because it's on the axis. M2, its shortest possible distance, is represented by R2 in this picture, which is just the entire length of the rod separating them, so that would be L. So for the first one, in situation A, what we have is that I is just ml squared. So even though m1 doesn't contribute anything, you still have a relatively large moment of inertia of ml squared because m2 is so far away. Now let's check the other situation. Do you think B is going to be more or less? Neither mass is on the axis, so some people think maybe it's going to be more, but they're both closer too, so maybe it's going to be less. Interesting. Let's see. So in situation B now, R1 and R2 both equal L over 2. They're both half of the rod's distance away since the axis is through the center. All right. Keeping in mind, again, R1 and R2, the radius values in this equation here are always the shortest possible distance. You could draw some crazy line from like way up here down to M1 and be like, oh, look, I could call R the super long distance of like 3L away. But no, that's not the shortest possible distance. That's not the perpendicular distance away. So plugging this in now, you got L over 2 squared, L over 2 squared. L over 2 squared is L squared over 4. So you have ml squared over 4 plus ml squared over 4, and you end up with 1/2 ml squared. So in orientation A, even with one of the masses on the axis offering no rotational inertia, you have double the overall inertia as you do in situation B. So it's tricky, but distance matters more than mass. That's why we see this difference. All right, so here's a question for you all based on what we've been talking about so far. Imagine you have two cylinders. One's a solid cylinder and one's a hollow cylinder. All right, now let's assume that they both have the same mass. So MH and MS are equal. And let's assume even that their radii are equal. RH and RS are equal. If I were to release them both from rest at the top of a ramp, which one would reach the ground first? Oh, interesting. So we did a problem a conceptual question that had to do with two objects reaching the end first, and our explanation was to determine which one had the greatest translational speed at the end, figure out which one gets there first, right? So maybe that's a hint for you. Pause it and try to figure it out. I want you to prove it to me using this idea of inertia. All right, so let's check it out. What do you think? Which one? Hollow or solid or the same? Well, hopefully you decided that the solid cylinder would reach the ground first. The simple explanation is, as we talked about earlier, 1/2 mr squared is the moment of inertia for a solid cylinder. Just mr squared is the moment of inertia for the hollow cylinder. So the hollow one has more inertia, therefore it's going to be more resistant to a change in motion, therefore it's going to reach the bottom moving at a slower speed, right? So that's one way to think of it. I'm going to prove to you using conservation of energy that that is indeed accurate. So thinking about conservation of energy, right? For each cylinder, your final energy is going to be whatever translational kinetic energy you have plus your rotational kinetic energy. Notice we now have two types of kinetic energy that an object can have. In this case, since it's moving and rolling, it's going to have both. And then plus mgh, which as you can see, h final is going to go away because it's 0. And that equals 1/2 mv initial squared plus 1/2 I omega initial squared plus mgh initial. So h initial is just our starting height. V initial and omega initial are both going to be 0. And so what we're left with is just our final kinetic energy is equal to mgh. That's true for both cylinders. Let's take this a step further though. If they're rolling without slipping, guess what? We know that V equals omega times R. So omega equals V over R. So we can make that substitution. Omega equals V over R, and since it's omega squared, you get V squared over R squared. And so you can factor out and solve for V, and what you find is that V final is just the square root of 2 mgh. So that's the same for both cylinders, divided by m, which is the same for both cylinders, plus I over R squared. Since we said R was the same for both, it's just whichever one has a larger I value is going to have a smaller final velocity, right? So since the hollow cylinder has a larger I value, its speed when it gets to the bottom is going to be slower, and therefore it will get to the bottom last. So smaller moment of inertia, the hollow cylinder reaches the bottom first. You could do this race with lots of different objects, and again, it's just about the moment of inertia to determine which one gets to the bottom first. Cool. So that's the idea of moment of inertia and kinetic energy, two really important issues and ideas to understand that you're going to get to practice with a lot as we move forward. It's really just adding one more small level to all of the conservation of energy stuff we mastered in chapters 7 and 8. So the next thing I want to talk about then is Newton's second law. So if you remember, Newton's second law told us net force equals mass times acceleration, right? So guess what? We can have a second version of Newton's second law that talks about angular acceleration. So what do you think it is that causes something to experience an angular acceleration? Well, maybe you guessed it. The answer is torque. If an object experiences a net outside torque, it will experience an angular acceleration. So what is torque? Well, you'll see real shortly, but torque again is any force that causes something to rotate. So if I applied a force out here at the edge of my door would want to rotate. If I applied the same force closer to the axis and further away from the doorknob on the same door, it will still want to rotate, but it'll be harder. It won't rotate as rapidly. It won't have as much acceleration because my force is so close to my lever arm, right? Or my lever arm's so short, it's so close to my axis. You do not have a large amount of leverage, and so therefore it's not going to rotate or angularly accelerate as fast. And if for some strange reason you started pushing inwards towards the hinge, a force along the axis of the door, in that case then you're probably not going to cause the door to rotate at all. So each of these are the identical forces being applied to the exact same door, but each one generates a different amount of torque. So how do we define torque? Well, that's a good question. The equation for torque is the magnitude of your force that you're applying multiplied by what we're going to call the lever arm distance. Now, lever arm distance sometimes confuses people a little bit, but really all we're doing is we're finding torque because it's going to be the product of our force and the distance that force is away from the axis of rotation. And so you can either find this by finding the component of the force that's perpendicular to the lever arm, the perpendicular distance, or you can find the whole force multiplied by the lever arm distance. So here you have your entire force that's perfectly perpendicular to our door. So our lever arm distance is the width of the door, and the force component perpendicular to that is just the entire force. So it would just be F times L. Whereas over here, if you apply this force at an angle, the perpendicular distance, the lever arm distance, is the shortest possible distance between that force and the axis of rotation. But if you notice, the force is way over here, right? And our axis of rotation is over here. So what is my perpendicular distance? What does that even mean? Because this is the only distance that I can think of from the axis to where the force acts. But the lever arm distance is the perpendicular distance from the axis to what we call the line of action of the force. A line of action is if you were to just take a line and extend it to infinity in both directions and run it exactly through your force, it's just a line representing the direction of your force. And your lever arm distance is the shortest possible distance, or the perpendicular distance, from your axis to that line of action. So it's not about where the force is acting, it's the distance to the line of action of the force. So for example, this force acting along the door's edge, it's touching the door at the very edge over here. So the force is acting at the door width away from the axis. But if you were to extend the line of action through that force, it runs right through the axis of rotation. Therefore, the lever arm distance is 0. Okay? So what we're dealing with here is the force times the perpendicular distance. All right? So you just must make sure, no matter what, when you're calculating torque, your force and your distance are always at a 90-degree angle to one another. They must be perpendicular. Okay? And you'll learn later, once you've taken Calc 3, the second way to define torque is as what's known as the cross product between force and distance, which will really help with more complicated situations. So the units that you're going to see here are newtons multiplied by meters. Keep in mind now, our newtons and our meters are perpendicular to one another. Okay, so before, back in chapter 7, we took newtons and multiplied it by meters when they were parallel, and we got joules. Now that they're perpendicular, we do not get joules, we just have newtons times meters. Okay, you only get joules when they're parallel to one another. Tricky. All right, so here's a series of 3 different forces, F1, F2, and F3. All right, let's say that they're all the exact same magnitude. How do their torques compare to one another? Well, the torque from force 1 that's pulling on this little weird kidney bean shape at this edge here, if we extend its line of action, it goes all the way through here, as you can see. And so the shortest possible distance, the lever arm for force 1 would be L1. And so the torque here, it's going to be force F1 times L1, and it's going to make it rotate counterclockwise, so we have a positive torque from torque 1 of L1 times F1. Force 2 is going to be F2 times L2, because here we see the line of action of force 2, right? And so this is the perpendicular distance, but that is going to be a negative torque as it makes it rotate clockwise. And F3, if you extend its line of action, it goes through our axis of rotation, which we're told is at point O. And since it extends through the axis of rotation, its perpendicular distance is 0, therefore its torque is 0. And that makes sense, right? It will not make it rotate if this is your axis of rotation. So it makes sense its torque is 0. Okay? Cool. So here's 3 forces, A, B, and C. Which of these forces generates a torque? Which one doesn't? All right, I'm guessing you figured out already A and B both generate positive torques on this bolt here as you're trying to loosen it, lefty-loosey, right? And FC does not, because its line of action runs through the axis of rotation. Now, which of these 3, if they all were equal magnitude, has the largest possible torque? Which one's most likely to loosen the bolt? Well, the answer to that would be FB. Because if they're equal magnitudes, FB has a longer lever arm distance, and therefore it's easier to cause it to rotate. That's why, I don't know if you've ever seen, but like a plumber will have like a tool that they can slip over their pipe wrenches that just extends your lever arm distance even further to increase their likelihood to loosen a given bolt. All right, so let's do a quick example problem here. I want you to figure out for me what the what the torque is that's generated by the Achilles tendon on the ankle. So here's our ankle joint here. Here's the Achilles tendon attached at point B. All right, doctors and medical students have kind of quantified that the approximate average distance from the ankle joint to point P, where the Achilles tendon attaches, is 3.6 times 10 to the negative 6. 3.6 times 10 to the negative 2nd power meters, 3.6 centimeters approximately. Okay, that's the distance from the ankle joint to point P, but the direction of the force is not perpendicular. Okay, so what we see here is that the direction of the force is about 35 degrees off of that measured distance. So therefore the lever arm distance, if we were to make a little right triangle here, is 55 degrees away from the measured 3.6 times 10 to the negative 2nd meters. Okay, so with that information, I want you to tell me the magnitude and direction of the torque acting on the ankle joint. So torque is force times lever arm, right? So first you need to find the lever arm distance, which I'm going to call lambda here, or you could call it L or whatever you want to call it. But the lever arm distance, lambda, is going to be this distance here, the hypotenuse, times the cosine of 55. And so then our torque is going to be equal to the force times the lever arm distance. So you do the math and you get 15 newtons times meters, but it's in the clockwise direction. It makes the foot want to rotate clockwise, therefore it's a negative torque. So our correct answer is negative 15 newtons times meters. All right, so now I want to expand our understanding of torque and try to tie it back to Newton's second law. So if you remember, Newton's second law tells us that force equals mass times acceleration. All right, so here we have some object, let's say it's experiencing a tangential force. So its tangential component of its force will equal its mass times its tangential component of acceleration. And now remember, torque equals force times perpendicular distance. So in this case, the perpendicular distance is the radius. All right, so then torque, force times perpendicular distance, substituting in Ft equals m times acceleration in the t direction, you get torque equals ma times r. And now tangential acceleration equals r times alpha. So if we substitute that in, we get the torque for a given point mass, just a single object, is mr squared times alpha. And now if you had a rigid body, again, like a bike tire or just any old object, then you're going to have a bunch of different masses with different moments of inertia, right? So again, here, this mr squared is the inertia, right? So if you have a rigid body with a bunch of different objects, you would really just need to add up all of the different torques from each different chunk of mass using calculus to do it most thoroughly, integrating over your entire object. And so you'd get adding up of all the torques is just going to equal the adding up of all the moments of inertia times alpha, since alpha is the same for all parts of that rigid body. And so what we find is a new definition of Newton's second law as it applies to rotational motion. It's just going to be equal to the net torque, or it's just going to tell us that the net torque is equal to your moment of inertia multiplied by your angular acceleration. So let's see, Newton's second law, as we learned it originally, told us that sum of the forces equals mass times acceleration, net force equals ma. Now we have net torque equals I times alpha. If you notice, almost every equation that we've tackled in the first 8 chapters of the book are now popping back up, replacing the translational or linear variables with rotational variables. So keep in mind, once again, our units for angular acceleration are radians per second squared. Real quick, I don't know if we mentioned this explicitly or not. What are the units for I, moment of inertia? Anybody know? Hopefully you do. The units for moment of inertia should be kilograms mass times meters squared. So moment of inertia has units of kilograms times meters squared. You multiply that by radians per second squared, and then you get newtons times meters. All right, so here's a kind of a trickier example problem we're going to kind of do together real quickly before talking about work and then wrapping up the chapter. So let's say that you have a dual pulley. I'll show you a picture here in a second, but a dual pulley is basically a pulley that has 2 different kind of wheel hubs that you can wrap things around. In this case, you have a larger wheel with a radius of 0.6 meters and a smaller one of a radius of 0.2 meters. And it has a total moment of inertia of 50 kilograms times meters squared. So it's a pretty large object, okay? Now you have a crate, an overall crate that has a mass, or excuse me, a weight of 4,420 meters that you're trying to raise up using this dual pulley, and you have a motor that's able to generate a tension force of 2,150 newtons. So we're using this dual pulley, we're using mechanical advantage to lift a heavy crate with a force that's less than half of the weight of the crate. And because the dual pulley, we're able to cause it to accelerate upward. So the question then is, what is the angular acceleration of your pulley? So here's the situation, just so you understand, with some free body diagrams. We have this dual pulley. The crate is tied to the inner radius, 0.2 meters, and the motor is tied to the outer radius, 0.6 meters. If we were to look at our pulley then and do a free body diagram, it's going to have 4 forces acting on it. Its own weight, the tension from the crate, T2, the tension from the motor, T1, and then the normal force at this axis, which I'll just call P. And if you notice, the normal force is going to be at an angle because the motor's pulling it one way and weight's pulling it down, and so the normal force must resist both of those. And then for the crate, pretty easy, just weight down, T2 going up, and then the acceleration upward as well. So now, with these types of problems, you must follow the same process that we've done before. Free body diagram, good pictures, labeling your variables, as we've done some of here, and then you do sum of the forces, and now you can add a new equation, sum of the torques, to try to solve. So let's look at how this would go, and maybe you should pause and try to solve it yourself, and then continue and watch me solve as you're about to see here. So to solve this problem, I want to do sum of the torques on my wheel or my pulley and sum of the forces on my crate. Since the pulley's not moving, the sum of the forces is going to be 0 in all directions, but sum of the torques is going to equal I times alpha. For my crate, it's not rotating, so sum of the torque is 0 for it, but sum of the forces will be equal to ma since it's accelerating. So starting with the crate, sum of the forces equals ma, so you have T2 minus mg equals ma, where this m represents the mass of the crate. Now for the pulley here, oh weird, okay. So for the pulley, sum of the torques is equal to I alpha. These lambdas represent the length L1. For some reason, the new version of PowerPoint changed my L to a lambda, so I apologize for that. But you can see that the torque is just force, so T1 times the perpendicular distance, lambda 1, which is 0.6 meters, minus T2, which is going down, times its perpendicular distance, lambda 2, which is 0.2 meters, and that equals I alpha. So when you first look at this problem here, what do you got going on? Well, we know that T1, or excuse me, the two T2s are the same value, but we don't know what T2 is, do we? Some people just want to say it's equal to the weight of the crate. Not true, right? T2 equals the weight of the crate plus ma. So we don't know T2, but we do know these are the same. T1 we are given, right? If we flip back to the problem statement, T1 is, boom, 2,150. So we know T1, we don't know T2. Lambda 1 is 0.6, lambda 2 is 0.2 meters. I we're given 50 kilograms times meters squared. We know the mass of the crate by dividing its weight by 9.8, but we don't know the acceleration or alpha. So at first glance, it looks like we have three unknowns, A, alpha, T2. But guess what? We can relate alpha and A together, as I'll show you here in just a second. So I solve one equation for T2 and substitute it into the other equation, and then I make the observation that the acceleration of the crate going up is just going to be the acceleration of this rope, which is equal to the tangential acceleration of the pulley at this location. And we know tangential acceleration is just alpha times r. The radius value at that point is just 0.2 meters, lambda 2. So now we can substitute this in for acceleration, and now doing that, making that substitution in here, we are now able to solve. So just so you're clear, in case this is confusing, I'm going to take T2, plug it into this equation here. That's what this is. T1 times lambda 1 minus T2 times lambda 2 equals I alpha. That's our same equation. Now I'm going to substitute in, instead of AY, I'm going to put lambda 2 times A. So I plug that in. And now my only unknown in this equation is alpha. So I do some algebra, solve for alpha, plug in all my numbers, and I get a box-worthy answer of 5.97 radians per second squared. So if I went a little quick, I'm sorry, but go ahead and rewatch the video and double check the math, but this should work out and you should get 5.97 radians per second squared, and it's positive because the motor wins and rotates the system counterclockwise. All right, the last thing I want to define for you quickly here before wrapping up this video is work. So if you remember from before, work was force times perpendicular distance. So here, if you have some force that's causing an object to rotate, then the perpendicular distance that it's moving, the parallel distance that it's moving is just the arc length, right? So force times parallel distance is work. Force times perpendicular distance is torque. Sorry about that. So work is force times parallel distance. The parallel distance is just the arc length that it rotates through. Arc length is just r times theta. We learned that at the beginning of chapter 10. So we can make that substitution, right? That S equals r times theta. So work is force times radius times theta. Well, force times radius, that's torque. So we can redefine torque as, redefine work as torque times theta. So before, work was force times displacement. As long as they're parallel, now work is torque times angular rotation. So a new way to define work is torque times theta. All right, so rotational work is torque times theta. Rotational kinetic energy, 1/2 I omega squared. Newton's second law in rotational terms, net torque equals I times omega. These are all our new different variables and equations for rotational motion. You'll get to practice those in homework, and I'll do some more practice problems for you in separate videos. Hope you guys have a great day, and let me know if you have any questions.